In today's video, I'll be taking you through this very interesting topic, homogeneous and heterogeneous equilibria. Okay, why should you watch this video to the end? At the end of this video, you'll be able to explain in details what we mean by homogeneous and heterogeneous equilibria. And also, you'll be able to solve questions on the calculations on homogeneous and heterogeneous equilibria. Under the heterogeneous equilibria, I'm going to teach you how to calculate the pH and pOH of solutions. And I'm also going to be teaching you how to calculate the solubility product of spiny soluble salts. All right. Now let's talk about homogeneous equilibria. Now, equilibria is the plural form of equilibrium. So we're talking about equilibria, we're still talking about equilibrium reactions. So now, homogeneous equilibria are equilibrium reactions in which all the species present in the reaction system are all in the same physical state. That is, the reactants are the product are in the same physical state. And as a result of that, it is easy for us to calculate the amount of any of the species present at equilibrium. Now, for us to do that, let's let U and V be the initial mole of the reactants A and B, respectively. And let X be the amount of A and B converted to these products, C and D. Now, we're going to be classifying this homogeneous equilibria in two folds, and I'm going to give an example in each of the two folds or cases. Now, let's look at case number one, when no initial amount of product is present and all species are 1 mole, all right? Now, so this is the initial mole of U, or U and V are the initial mole of the reactants A and B. And of course, no initial amounts or moles of C and D are present. Now, if at equilibrium, X amounts of the reactants has been converted to the products. So therefore, X are the amounts of the product at equilibrium. Then, of course, because they are being produced from the reactant, then the amount of the reactant is reduced by those amounts of the product formed. Okay, now that's case one, when they are all in 1 mole and there is no initial mole of the product. Now let's look at what that's going to give us. Of course, we write the Kc for this reaction, and that's going to give us Kc going to be the concentration of the products over the concentration of the reactants. And of course, you know that the reactant, this concentration, the square bracket, it means concentration. So this square bracket C means concentration of C, square bracket D means concentration of D, square bracket A means concentration of A, square bracket B means concentration of B, right? Now, so at some equilibrium, of course, the Kc will involve the amount at equilibrium. So this one, concentration is actually mole over volume, okay? So therefore, what is the mole of the product at equilibrium? That is X over volume. And what about this D? It is X over volume. And then, of course, we have A, which is the initial mole minus X over volume. So this one is V minus X over the volume, all right? So, and so you'll be able to calculate the Kc respectively for each of the mole. Of course, the fact that the volumes are also, which is S squared over V squared divided by U minus X over V, then V minus X over the volume, okay. Now let's go to case 2. The case 2 is when no initial amount of the product is present and all the species are not 1 mole, okay? Are not 1 mole each. Now, so of course, this is the initial mole of the reactants. So U is the initial mole of the reactant, V is the initial mole of the reactant B, and 0, of course, no initial amount of the product is present. Now, at equilibrium, what happens is X amount of the product has been formed. Okay, so, and of course, the reactants will decrease by this X. But I want to call your attention to something very important, and that is the fact that this X amount of product is affected by the mole here, by the mole. And of course, the amount that leaves from this initial amount of V is affected by the mole of B. The amount that leaves from here is affected by that. So that's just the difference between when it is 1 mole. Okay, of course, can you see this one is 1 mole? So 1x. Here is 1x. So it's B minus 1x. And so if you're actually dealing with a reaction in which, let's say this one is 2 moles, then this one will have been 2. Okay. And let's say this one is 3 mole, then this one will have been 3. So that's how it happens. Now, so the mole, but you have to note that X is the amount of the reactant that is converted to the products. And so we know that it's going to be affected by their moles. So that's just what matters. All right, so in this case, we'll be having Kc to be equals to cost concentration of the products over the coefficient of the reactant raised to the power of their moles. All right, and A is the power of the mole and B raised to the power of its mole. So, of course, this one is concentration, so and this one is in moles, so it would vary by the volume. Concentration of C will be the moles of C divided by the volume. Question number 1 says that 1 mole of hydrogen gas reacts with 1 mole of iodine gas at 25 degrees C in a 1 dm cube reacting vessel. Calculate the concentration of hydrogen iodine and hydrogen iodide present at equilibrium, given that Kc for the reaction is this. So now, of course, you see that this is an example of a question for homogeneous equilibria, because all the species are all in the same physical state. They are all gases. All right. So what you do is that you first write the equation of reaction. So we have hydrogen gas reacting with iodine gas to produce hydrogen iodide. Now you got to write the initial mole, then you write the mole at equilibrium. So of course, the initial mole, the given amount of this one is 1 mole, and this one is also 1 mole. And of course, we're not given any initial amount of the hydrogen iodide, so it is 0. Now we say that X is an amount of the reactant that has been converted to the product. So this X will be affected by these two, right? So we put the 2X here. All right, so here is 1 mole minus the X. So I'm not going to be writing 2X because this 2 is what affects this one. Here is 1. So it's going to be 1 times X. So here is also going to be 1 minus X, not 1 minus 2X, because the mole here is 1. All right, so now what is the initial concentration? What's the concentration of hydrogen at equilibrium? Of course, we see that it's also going to be it's also going to be equal to the amount of iodine at equilibrium. So we can do both together so as to save time. So here at equilibrium, which is mole over volume, and at equilibrium, the mole of each of them is 1 minus X. Volume is 1 dm cube, right? So we've divided, and that's going to give us 1 minus X mole per dm cube. So what about the mole of hydrogen iodide? It's going to be 2X over volume, so which is 2X over 1 dm cube. So that's going to be 2X mole per dm cube. Okay, so the formula for the equilibrium constant expression is this. That's HI squared divided by okay, so that's the expression for the equilibrium constant expression. So we having the concentration of the product over its mole, then divided by the concentration of the reactants raised to the power of their mole. Now, this case will be given as 45.9. So this one is going to be 2x squared divided by 1 minus x and 1 minus x. So those are the concentration of this other one. All right, so what do we do? We cross multiply. So we're going to have 4x squared to be equals to 45.9 minus 91.8x plus 45.9 s squared. And so we take we collect the reactants and then we make x the subject. That's going to give us a quadratic equation. And so that's going to give us 41 so, and that's going to give us x to be equals to 142 or 0.77. Now, which of them is going to be the correct formula? Which of the correct answer? Which of them are we going to pick? Now, we see that the initial mole of hydrogen gas is 1. So the x we're going to pick must not be greater than the initial mole of the reactant. So this x, 1.4, cannot be x. So therefore, s is going to be 0.77. Okay, so therefore, We put it into the equation. So we already know that the concentration of hydrogen at equilibrium is also equals to, okay, sorry. So this one should be in mole, okay? So that one should be in mole, calculate it in mole. Okay, so this one is actually equals to this one. So, and that is 1 minus x over volume. So, and that is actually equals to what? 1 minus 0.77 over 1 dm cube. And that's going to give us 0.23 mole per dm cube. So that's going to be the concentration of each of them. All right, and the hydrogen iodide at equilibrium is 2x over the volume as mole. So that's going to be 2 into 0.77 mole divided by 1 dm cube. And that's going to give us 0.5, I'm sorry, 1.54 mole per dm cube. I think that is very simple and easy for you to understand. Now let's go to example number 2. Example number 2 says that nitrogen dioxide decomposes on heating according to the following equation. When 4 moles of NO2 was put into 1 dm cube container and heated to a constant temperature, the equilibrium mixture contains 0.8 mole of oxygen. Calculate the numerical value of the equilibrium constant Kc. All right, so of course we know that Kc, let me first write the equation of reaction. We'll be having okay, pardon me, please. Now we have here two. Now the initial mole at equilibrium. Okay. Now, what's the initial mole of this? So we're given 4 moles. Now, what about the moles here? We're not given any initial amount of this. Now, what about mole at equilibrium? Of course, we say that this one is going to be, if this one is x, this one is going to be 2x, because these two will affect this here is 1 times x. All right, so here 4 minus, then this 2 is going to affect the x that is leaving this place, so that's going to be 4 minus 2x. I believe you understand that, right? You follow the model I gave at the initial start of this video, you will understand. All right, we know that Kc is the concentration of the products over the concentration of the reactants. No, that's going to be the mole. So this one at equilibrium, of course, the concentrations here are the concentration at equilibrium if you are calculating Kc, all right? So the concentration of NO, which is going to be 2x, but I need to emphasize that this question, look at it, look at this question, please. The question says that when 4 mole of NO2 was put into a 1 dm cube container and heated to a constant temperature, the equilibrium mixture contains 0.8 mole of oxygen. Now, the equilibrium at equilibrium, we have 0.8 mole of oxygen. So it means that this X is 0.8. All right, so X is 0.8 moles. So that is the amount of hydrogen that is present at equilibrium. So in a question like this, if you are asked to calculate the equilibrium constant, it means that X must have been given to you indirectly in the question, which you have to sort it out. But you writing it out, following the template this way, makes the calculation very easy for you. Okay, so now, mind you, this one is actually the mole of NO at equilibrium divided by volume, and of course the mole of this is 2x divided by, so 2x mole divided by the volume. So, and the volume, so what is x? X is 0.8 mole, and the volume is 1 dm cube. So of course this one is going to give you 0. Oh, sorry, this one is going to give you 1.6 mole per dm cube. Okay, so now the mole, the concentration of oxygen at equilibrium, that's going to be a mole of oxygen at equilibrium divided by the volume, and that is X divided by the volume, so which is 0.8 mole divided by 1 dm cube, and that's going to give us 0.8 dm cube. Now, what about the concentration of NO2? So, which is the mole at equilibrium divided by the volume. So, the mole at equilibrium is 4 minus 2x divided by volume. So, and that's going to be 4 minus 2 into 0.8 divided by 1 dm cube. And that's going to give us that's 2.4 mole per dm cube. So therefore, we can now calculate the Kc. Kc now is everything here. That's going to be NO2, which is 1.6 squared times 0.8 all over 2.4 mole per dm cube. And of course, when you press your calculator, you're going to get 0.355. All right, so we talk about heterogeneous equilibria. What is heterogeneous equilibria? Heterogeneous equilibria are equilibrium reactions in which the reacting species are not in the same physical state of matter with the product. So the reacting species and the products, both the reactant and the products, are not in the same physical state of matter. We're going to be having these examples, number one, and we're going to be dealing with the calculations under them. So the dissociation of water. So, and of course, when you're talking about the dissociation of water, yeah, in liquid state, liquid. So it dissociates to OH minus aqueous and hydrogen ion aqueous. Okay, now, and also we're talking about dissolution of sparingly soluble salts. Now, for instance, those salts that are not readily soluble in water, like silver salts, most silver salts are not soluble in water. The one that is soluble is AgNO3. So it's only the AgNO3 that is readily soluble. The others are not soluble in water. Now, when you have AgCl, for instance, by the time you put AgCl in water and you shake it several times, you shake it, it won't dissolve, you shake it and even shake your body, nothing will happen. So, and but what happened is that an infinitesimal amount of this salt actually dissolve to form AgCl aqueous, but you wouldn't notice that. So, and this one aqueous. So this is solid and these are aqueous. So that is the reason why it is heterogeneous equilibrium. Now let's talk about more about dissolution of water. Okay, so now for the dissolution of water, let's come up with something here. Okay, so when you're talking about water as H2O liquid, it's going to give us OH minus aqueous plus hydrogen gas aqueous, hydrogen ion aqueous. Now, if I should write the equilibrium constant expression for this, the equilibrium constant expression here is going to be written in form of Kw. So, and of course, the concentration of products over the concentration of the reactant. Now you see that the reactant is a liquid, and because it's in the liquid state, it can't, it can't appear in the equilibrium constant expression. So this is what you have, all right? Now at 25 degrees C, the Kw is actually 10 raised to the power minus 14. And so we have 10 raised to the power minus 14 to be equals to OH minus and H plus, okay? Now, let's take the minus log of both sides. Take minus log. Okay, now, okay, before I do that, this is going to be the relationship that will exist between the hydrogen ion and the hydroxyl ion. So the multiplication of the hydroxyl ion by the hydrogen ion is going to give us 10 raised to the power of minus 14. Now, if you take minus log of both sides, so what do we have? We have minus log 10 raised to the power of minus 14 is log, or minus log concentration of OH minus and H plus. So we're going to be having this one. What's going to give us? Okay, so this one is going to give us 14, all right? And of course, this one is going to give us minus log OH minus plus minus log concentration of hydrogen ion. And of course, so this one is going to be 14 equals to, what is minus log this one? So this one is going to be POH plus pH. So where POH, now mind you, this one is a small letter, so this one is OH, so small letter POH, so is minus log what? OH minus. Okay, so and pH is minus log H plus. I think that is very interesting. So this is small letter P and this is capital letter H. So therefore, the addition of POH and with pH is going to give us 14. So this one is going to be equation 2. And of course, this one is going to be equation 3. And this one is going to be equation 4. I think life is very easy with that. Now, if these equations are well understood, then let's solve this question. So the question number 1 says, the hydrogen ion concentration of a solution is 2.5 times 10 raised to the power minus 6 mole per dm cube. What is the pH of the solution? The concentration of OH ion and POH. Okay. Now, okay, so how do we solve this question? The question says that the hydrogen ion concentration of a solution is 2.5 times 10 to the power minus 6 mole per dmK was the pH of the solution. And what is the concentration of OH minus ion and the pOH of the solution? All right. Now, of course, we know that pH is minus log the concentration of hydrogen ion. And from the question, we'll be given the concentration of the hydrogen ion as 2.5 times 10 raised to the power of minus 6. And so that is 2.5 times 10 raised to the power of minus 6. And so what would that give us? So we will have when you press your calculator, you are going to get 5.6. Okay, so now the question number 2 says that we should calculate the concentration of the hydroxyl ion. So you will know from the equation number 1 that the hydroxyl ion multiplied by the hydrogen ion gives 10 raised to the power of 14. And so we just apply that. So this is what we are looking for. And that is going to give 4.0 times 10 So that's 4.0 times 10 raised to the power of minus 9 mole per dm cube. So the question now says that you should calculate the pOH. Of course, you can say that pOH, which is minus log the concentration of OH. Or you can as well use the formula of pH plus pOH equals to 14. And of course, if we're going with this, so we say that pOH is going to be 14 minus pH, so which is 14 minus 5.6. So that's going to give you 4.4, all right? Okay, sorry, so 9.4 rather, 9.4. Okay, now, I believe this is actually very simple. Of course, you could have as well used the formula of pOH equals to minus log OH, and so you would have gotten that's minus log 4.0 times 10 to the power minus 9, and so that should give you 9.4. Okay, so now if this is actually very true, oh sorry, 8.4, 8.4. Now, if Ka is you were given this question 1.85 times 10 to the power minus 5, and you have to find pKa. How do you do that? pKa. Now, from the earlier discussion, you can see this P in chemistry, this small letter P means minus log. So you are given pKa, Ka, and you have to calculate pKa. The solution is simply saying that you should take the minus log of Ka. So if you see a man and they say, what is P man? So P man means the minus log of man. All right. So I think that is very simple. Now let's have another question. Calculate the pH of 0.0 0.01 mole per dm cube HCl 0.0005 mole per dm cube H2SO4 0.0005 mole per dm cube calcium hydroxide. Now, when you have to calculate the pH of an acid or a base, now, so what you have to do first is to dissociate the acid and the base. And so you know the concentration of the hydrogen ion or the hydroxy ion that is present in the acid or the base. All right, now the first question is to calculate the pH of this solution. So what we're going to do is to first dissociate the acid. So we have HCl giving us H plus Cl minus. So here is 0.01 mole per dm cube, which I can write as capital letter M. All right. So what about this? So you dissociate it, of course, you're going to have absolutely an absolute amount of this because it's a strong acid that will dissociate completely in solution. All right. So therefore, what do? So if 1 is here, then 1 times this, so it's 0.01 molar or mole per dm cube. And so this one too will be 0.01 mole per dm cube. Now, pH, of course, you know, is minus log the concentration of hydrogen. And so that's going to give us minus log 0.01. And that's going to give us 2. Now for number 2, or H2SO4, we have 2H plus. So we will have pH. So if this one is 0.0005, of course, this one will be 2 times 0.0005. So that's going to be 2 times, and that's going to give us 0.0001. And that's molar, or mole per dm cube. So and this one is going to be 0 because this one is 1 times this. So 0.0005 molar. All right. So therefore, the pH, which is going to be minus log concentration of the hydrogen ion. So which is what you have here, minus log 0. So when you press that on your calculator, so you're going to have 4, right? Now, so number 3, you will calculate the pH of this. So here is calcium hydroxide. I'm going to give you calcium 2 plus 2OH minus. Oh, sorry, pardon me. So if this is 0.005 mole per dm cube, so this one is going to be times 2 of it. So therefore, and this one is good. I'm sorry, this one is 1, 1, this one is 2, 2. So we have 0.0005 molar. And this one is going to be 0.001 molar. So now in this place, we can calculate the pH directly because this is a base. So what you have here is OH, so you have to calculate pH first. So for bases, what you do to get pH is to first calculate the pOH, so which is minus log the concentration of OH minus. So which is minus log the concentration, which is 0.001, which is 3. All right, so therefore we know that pH is going to be 14 minus pOH. So, and that is going to give us, that's from equation 2 earlier. So we see that pH is going to be 14 minus 3, and that is going to give us what? Now here is a question. Question says that calculate the hydrogen ion concentration, the pH, and the percentage dissociation of 2.0 mole per dm cube acetic acid if its dissociation constant is less. Now, there's this difference between a weak acid and a strong acid. Strong acid dissociates completely in solution, and that is you are expecting a 100% dissociation. And that was why we wrote the equation earlier for those acid we dissociated at the base. Now for weak acid, such as acetic acid, now there is something that you need to know, and that is very interesting. This one is going to dissociate by equilibrium because it is a weak acid. So acetic acid, which is ethanoic acid, this, so it's going to dissociate by equilibrium, and it's going to give you an acetate plus this. Okay, now this one is 2.0 mole per dm cube. What I want you to know is that because it's a weak acid, this one is not going to be the same as, it's going to be less than, in fact, far less than 2.0 mole per dm cube. And this one too will be far less than 2.0 mole per dm cube because unlike HCl, or other strong acid, whereby you have 2 molar here, what you're also expecting here are 2 molar because it will dissociate completely, not following equilibrium. When you say this is not equilibrium, so here is equilibrium because this one is dissociating by equilibrium, all right, because it's a weak acid. Okay, so I'm still going to teach this topic in the part 3 of this topic, whereby I'll be discussing acid equilibria. I'm going to treat it in a special way, where I'm also going to be talking about buffer solution. So now, but we are going to use a formula to get this, to get the amount that should be here. So if this one is X is unknown, so what happens here is that this X, which is the concentration of the hydrogen plus, is the square root. I'm going to teach you how to derive this equation later. And that's the acid dissociation multiplied by the concentration of the acid. So the acid dissociation constant is what you have here, all right? So therefore, we want to calculate the concentration of the acid now. So it's going to give us the square root of the acid dissociation constant, which is 1.85 times 10 raised to the power of minus 5. And what is the concentration of the acid? So from the question, we can see that it is 2.0 mole per dm cube, all right? So, and that is going to give us what? 1.92 times 10 raised to the minus 3 mole per dm cube, all right? Now, so what about the pH? Of course, we know that pH is minus log of the H, and that is actually minus log of 1.92 times 10 raised by minus 3. So you just press your calculator and get that. Now, the question number 3 says that the precipitate dissociation so, of course, the precipitate dissociation is actually the concentration of the hydrogen ion divided by the concentration of the acid multiplied by 100. So, of course, so this one is 1.92 concentration of the acid, which is 2.0, then 10 raised to the 100, right? So what's that going to give us? It's going to give us 0.92%. Can you see how low the percentage dissociation is very low percentage dissociation. So just 0.92% of this, just 0.96, sorry, this is 0.96% of 0.96% of the acid produced or dissociated. So the other did not dissociate. So that's a very low dissociation. And so therefore, it is a weak acid, right? Now, I have something for you today. It's very special. Today is the Valentine Day, where everybody is talking about love. Of course, many people have turned a day like this to a day of sin, a day of sexual immoralities all over the world, but that's not the purpose of today. Now, when you see this Valentine, you see it in John chapter 3, verse 16. That's why I'm sharing with you about this love story. For God so loved the world that he gave his only begotten Son, that whosoever believes in him should not perish, but have everlasting life. Now, why is it that God gave us his only begotten Son? Why did they call him the only begotten Son? It was called the only begotten Son because his birth did not come from the sexual activities of a man and a woman. His birth came by the power of God. That's why Jesus Christ is called the only begotten Son of God. And so he God, and that is someone that is so unique to God, because God deliberately sent him into the world. He's someone who God, gave him a special privilege, to be born of the Holy Ghost. And so God gave him to the world. Why did God give him to the world? God gave him to the world because in the book of 1 John chapter 3 verse 8, he said, he that commits sin is of the devil. For the devil sinned from the beginning. The devil has committed sin from the beginning because he thought of exalting his throne above God. And so when, the devil committed sin, God prepared hellfire, everlasting fire prepared for the devil and his angel. And that's what we see in the book of Matthew, chapter 25, verse 41. That hellfire is prepared for the devil. And because he that commits sin is of the devil is of hellfire, then everyone that commits sin will go into hellfire. And in the book of Hebrews, chapter 9, verse 22, and without shedding of blood is no remission. There is no remission of sin without shedding of blood. Of course, we saw it from the journey, from the life of Israelites, from the beginning of their lives. They will have to shed blood before their sins can be remitted. And so, but God commended his love towards us in that while we were yet sinners, Christ died for us. Christ shed his blood for us. God commended his love to you. God commended his love to me, that while we were yet sinners, Christ died for you and I. He gave up himself. He shed his own blood so that your sin, my sin, can be remitted. And that is why today, will you accept this love? Jesus. For God so loved the world. That's today's Valentine. That today's Valentine 2024, you are going to have it in your account that you accept the love of God that is sent to the world. For God so loved the world that he gave his holy begotten Son, so that you can escape hellfire, so that you no longer be of the devil. Because he that commits sin is of the devil. That you give your life to Jesus, you repent of immoralities, you repent of lying, of sinning, and you give your life to Jesus. And then Jesus will take you by the hand and will take care of you. Since 2004, that's about 20 years ago, I gave my life to Christ. He has been good to me. Have heard his voice. I have heard his kindness. I have seen his kindness. I've seen his goodness. And he has bared me on eagle's wings. He can do that for you. Accept this love today. Accept this love that will save you from penury in this world and in the world to come. I pray that you'll be wise, you'll be smart, you accept this Jesus today in Jesus' name. God bless you wherever you are. You can go on your knee and ask Jesus to come into your heart. You can ask that Jesus accepts your love. You love me. Even while I was yet a sinner, you commended your love for me and you died for my sin. Come into my heart today. Save my soul. In Jesus' name I've prayed. Lord Jesus, as many that have heard this word, I pray that you save their soul. I pray that you bless their life. I pray that you turn them around. In Jesus' mighty name I've prayed. Amen. All right, I'm going to continue with homogeneous equilibria, and I'm going to be teaching us about the solubility of spinally soluble salts. Okay, so let's talk about solubility products. Now, these solubility products, what we're talking about here, for instance, if you have a spinally soluble salt like silver triazocarbonate 4, of course, this is a salt that when you shake and shake and shake, it's not going to dissolve, but an infinitesimal amount of heat, which you may not notice, will dissolve to produce this and this ion. Oh, sorry. Sorry about this. So you have Ag2CO3 solid, so which is going to produce two of this. So an infinitesimal amount of this salt is going to produce these ions. Now, if, of course, if X is the solubility of this one is going to be 2X, and this one is going to be X, okay? If X amount of this one dissolve, are you getting in? I don't want you to be confused. Of course, if you have 10 grams of this one, let X be the amount of it that dissolved, okay? And when it gets to this plate, this 2 is going to multiply it. All right, so it's going to be 2x here, and here it's going to be 1x. All right. Now, when we're talking about the solubility product, we're talking about the equilibrium constant. Of course, the equilibrium constant for this one is Ag plus raised to the power 2. Of course, the concentration of products over the concentration of reactant. So this reactant, we can't put it here because this is solid. It's only aqueous and gases that appear in the equilibrium constant expression. So therefore, you're going to have this one 2x squared x. Okay, so that's going to be 4s squared. So it now depends on the solubility of the salt or the amount of this salt that dissolved in the solution. Now let's have an example here. Let's have this very interesting example. The question says that the solubility of silver trioxocarbonate 4 is 1.30 times 10 to the power of minus 5 mole per dm cubed. Calculate what is the solubility products. So now the question is, the solubility of silver transcarbonate 4 is this. That is, the amount of the silver transcarbonate 4 that actually dissolve is this. Now say that what is the solubility product of solubility product of this salt? So of course you write it like this. You say let X be the solubility of the salt, and of course which is this, and this X, yeah, so X has been given to you as 1.30 times 10 raised power minus 5. So the solubility product is actually the equilibrium constant for the dissolution of this salt. So therefore, the KSP now, so which we have solved earlier as 4x squared. So that's going to be what? 4 into 1.3 times 10 raised power minus 5 raised power to the power of 2 or 3 rather. Sorry. So of course this one will be 3. It's to the power of 3. All right. So and that's going to give us what? 1.69 times 10 is to the power of minus 10. So then you know the unit is here. So you're going to be mole per dm cube raised to power 3 dm raised to power minus 9. All right. Now let's have another example. The solubility of AgCl at 25 degrees C is 1.30 times 10 raised power minus 5 mole per dm cube. Calculate the solubility products of the salts at this temperature. Okay, so of course, let X equals to the solubility of the salt. So what we have here is AgCl solid producing Ag aqueous plus Cl aqueous. Okay, that's chloride aqueous. Now, if the amount of this that dissolved is X, then of course, this one is going to be X, this one is going to be X. But write the K equilibrium constant expression for the process, of course, is going to be Ag plus and the chloride ion. So, of course, this one is solid to now appear in the equilibrium constant expression. So, this one is X, this one is X. So, but X has been given in the question because that's the solubility in mole per dm cube. So that's going to be 1.30 times 10 raised to the power of 5 mole per dm cube. So it's squared. Okay, since this one will give us S squared. And so when you press that in your calculator, you will have 1.6 oh sorry, that's more raised to power 2 dm raised to power 6. All right. I'm sorry, I think here there was a mistake. So here should not be this, it should be higher than this. So if you press your calculator very well, you're going to be having 8.79 times 10 raised to the power minus 15. Raised to the power minus 15. That's mole cube dm raised to the power minus 9. So here is the question. Calculate the solubility product of calcium fluoride at this temperature. If its solubility at this temperature is this. Now what you can see here is that this is solubility in gram per dm cube, that is mass concentration. Okay, so now let X equals to the solubility product, solubility of the so we dissociate this calcium fluoride solid. So this is aqueous, this is aqueous. So if the solubility of this one is X, this one is X, this one is 2X, and of course we have the KSP, which is concentration of calcium ion and fluoride raised to the power of 2. And of course, this one is going to be X, and this one is going to be 2X squared, and that is 4X cubed. So where X is 0.36 gram per dm cube. All right. Now, but we have to convert it to mole per dm cube. It must be solubility in mole per dm cube. Okay. So therefore, we will find the molar concentration. Remember that molar concentration is mass concentration divided by the molar mass. So, and of course, the molar mass of calcium fluoride, because calcium fluoride, that's going to be 40 plus 2 times 19, and that's going to be 78, all right? So we're going to have this one, 0.36 gram per dm cube divided by 78 gram per mole. So, and that's going to give us 5.0 times 10 raised to the power minus 3 mole per dm cube. All right, so of course the KSP, so which is 4x cubed, and so you put this value into X, it's going to give you all right. So when you press your calculator, so what are you going to get? So that's going to give us pardon me, so that's going to give us 5.0 times 10 raised to the power minus 7. So that is more raised to the power of 3 dm raised to the power of 9. Yeah, I believe you've gained something in this video. If you gained something, like this video, share it with your friends having difficulties in these areas, your siblings having challenges in this area. So share with everyone, subscribe to my channel, and thank you so much for watching to the end. If you need any tutorial, an online tutorial, I'm available. Check me on this number through WhatsApp. Introduce yourself and how you come about my number. So, and then we'll talk about that. All right. Thank you so much for watching to the end. And if you have also given your life to Jesus and you want more encouragement, counsel, you can also reach me through that number. Thank you very much. Have a very wonderful day ahead.